Last time, we had spent some time in class reviewing some geometry concepts that would be kind of like foundational to what we're doing in trigonometry, or at least the start of trigonometry. Chapter 2, really, but I'd like to kind of continue that. Today we'll do some specific example things, and then we'll do that first Delta Math assignment in class. So if there's any questions on stuff, I think some people might have already started it. That's okay, not a big deal. And we'll talk about how Mr. Kulik will be grading that first one. And then we'll probably start chapter or section 1 or chapter 1 after that. Sound good?
Yeah.
Okay. So let's see. Make that a little bigger. So we'll continue with our geometry review. All right, let's say the direction here is just solve for x. And we'll call these all. So, what do we need to use in order to answer a question like this? Go ahead. Hold on. Olivia. No. Yes?
Rita.
Rita. You
I'm
switched.
taller than her.
That's why I got the names wrong. I'll make a note of that. That's okay. Next time, give me a heads up before I embarrass myself saying the wrong names. That's okay.
Yoti is Sokotoa.
Great. And what sine, cosine, or tangent, which one would be the one I'd want to use in this case?
Oh, cosine?
Mm-hmm. And how do we know cosine?
Wait, adjacent over hypotenuse.
Right. So relative to the angle that we're given, we have adjacent and hypotenuse that we are concerned with. So that's correct. So we'll say cosine of, and then what's going to go inside the cosine? Great. Always the angle measure equals, what do I write here? 8 over x. Very good. Thank you. So at this point, the geometry is done. This is now an algebra problem. So we're solving for x. Want to get the x by itself. First thing we do is multiply both sides by x. Very good. Again, we want to get the x out of the denominator because we can't really get the x by itself if there's a 1 over it stuck onto it. So I do that. And then next would be, great, divide both sides by cosine 36. Remember, cosine 36 is just one number, some big kooky decimal, but it's just a number. Everybody's still on board? And then what do I do from here? From the sound of things, everybody knows what to do here. It's calculator time, right? What do I have to be careful about with doing this on my calculator? Yeah, I have to be sure that I'm in degree mode. How do I know that I need to use degree mode rather than radian mode in this problem? How do I know that I need degree mode on my calculator as opposed to radian mode?
Because it's 36 degrees.
Because it says on the label of the angle that it's at degrees. Very good. These are obvious questions, but like we're going to just make sure everybody's on the same place by asking the really obvious things also, right? All right, so to make sure your calculator's in the correct mode, we'll press the mode button, which is right next to the blue second button. And you'll just want to make sure that the degree option is highlighted. If it's not, just use your arrows to move your cursor onto that degree and press enter to make sure degree is highlighted.
How did you do that page?
Press the mode button, which is right next to the blue.
Never mind, it isn't a degree yet. Oh.
Okay. And then I like to use most of our calculators have the option to write this that looks like the fraction that we've written on our sheet of paper. I'm going to use that option here. Not that it's that necessary, but it helps. So I'm going to press alpha and then the y equals button. That is a shortcut to the fractions menu. And to get the vertical fraction like that, I'm going to press the option number 1. And now it's going to look just like the fraction on my sheet of paper. Now this problem, the parentheses wouldn't have been much of an issue. But there's lots of times we write fractions where like it's bonkers parentheses trying to write it like with the division symbol. That's a very nice option to have. It's a nice shortcut to do that. And then it's much easier to get the parentheses right when it's already looks like it does on your sheet of paper, right? All right. So if I want this rounded to the hundredths, where would I write here? 9.89. Good. Ugh. Does somebody have a stylus that they're not using that I could use for the remainder of the period? Handy for me? Thank you very much. I'll make sure I return this to you, Sophia. I don't know what is up with my stupid stylus, but it's being stupid. And I'll just write here, calc. Again, I'm writing notes if you're going back and looking at this and like, how the heck did he get that? I just typed it to my calculator. If I wanted it to the 10th, what would I have written?
9.9.
9.9. Oh boy, I got to do this then, huh? Nope. And why am I putting the squigglies instead of a hard equal sign? Because we rounded, right? That's the approximate equal sign. I did that because I'm rounding. I won't be picky about that on your papers, but these are notes. They're for you. I want to make sure I'm communicating clearly that it's not exactly that number. I rounded to get that. Everybody's okay? Okay. You guys remember doing these? It's fairly straightforward. Okay. What if I have instead... Oops. Actually, I don't want it there. I'll put it there. What am I going to do here? Okay, still kind of the same problem, right? And why did I pick sine here then?
Because you know the opposite.
Great. Relative to the angle, I know the opposite and the hypotenuse. So the equation I'll write is going to be sine of x, good, equals, very good. Everybody happy with how we wrote the equation? If I'm going too fast or there's something you don't understand, please stop me. It's okay. All right. Algebra time. To get the x by itself, I got to get rid of that sign that's out front. How do I cancel out a sign? Good, the sine inverse. So we'll do sine inverse to both sides. Because sine cancels sine inverse. Oops, forgot to write my equal sign. And then it's calculator time, right? To type this into my calculator, how do I get the sine inverse? Second and sine, very good. And I'm not going to bother with the fraction command there because obviously like 8 over 12 is just 8 divided by 12. But if you want to, you can do that. So I get this number. If I want that to the hundredths, I would say
4181.
4181. Or if it was to the tenths, 41.8. Should put a degree sign there. Not a big deal if you don't, but you know, we're aiming to be precise, right? Say what we mean. I know, Mr. Kulik, I know. But I'm not penalizing. We're just trying to do better. You know what I mean? Okay. What if we want to... So what if I ask you to write the desired ratio exactly? So we are being asked to write the ratio for sine of A. Yes, Giselle. Great. Great. So relative to angle A, we need opposite and hypotenuse to do sine. So we have to use the Pythagorean to find BC. Uh-oh.
Please excuse this interruption.
No.
If any 9th or 10th grader has not had their school picture taken yet, their school pictures or their school ID picture taken today or Friday, I ask you to kindly come to the library so that we can quick take your picture and you can get your ID and be on your way back to class. Freshmen and sophomores, please come to the library if you do not have your ID card.
Okay. So Pythagorean theorem, a squared plus b squared equals c squared. What's the thing we have to be careful about when we're plugging numbers into Pythagorean theorem? Hajar, Rachel? Rita, that's an R something. Excellent, yes, hypotenuse must be c. So the c in this case is 13. Does it matter where the other numbers go? No. Okay. So I can then just subtract 7 squared from both sides and just say x squared is equal to 6 squared, right? No! Yeah, I saw some people shaking their head. What's wrong with what I just suggested doing? Why would I have to do that first? Order of operations, right? The exponent has to come before addition or subtraction. Very good. So we do need to make sure we're squaring these numbers before we're adding and subtracting. I know I'm just kind of saying some stuff, but we're just reviewing, right? Then we can subtract the 49 from both sides. Is that right? Yeah, that's right. No. Yes, okay, sorry. I could just, jeepers creepers, Mr. Bullock. It's the end of the day, you know? Trying to do mental math, sometimes you're like, yeah, no, yeah. Right? No. Anyways. Okay, so we have x squared equals 120. Anything else? Square root both sides, right? So I just say x is equal to, and I type that into my calculator, right? No, why not? Yeah, so it asks for the answer exact with reduced radicals. So I'm not going to just plug this into my calculator. I have to try to reduce this radical. Anybody remember how we need to do that? Yes.
You can split it up into something that is a perfect square, so you can take it out.
Excellent. So we're going to look for perfect squares that are factors of 120. Excellent. The perfect squares, give me an example of a perfect square. 4, sure. And then, 1, 9, 16, 25, yada, 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 right? Obviously, 1 is not helpful to us here because every number is divisible by 1. That doesn't really do much for us. But 4 is a factor of 120, so let's go ahead and pull that factor out. So 120 is 4 times 30. Can I take anything more out of 30? Are there any more perfect squares in 30? No, right? We can see right away that 4, 9, 16, 25, none of those divide 30, and obviously the next one's 36, and that's clearly not going to divide 30 because it's way too big. Of 30? Yeah, we're going to do that. I just was seeing if there was more perfect squares hiding anywhere. But yes, so we should remember that we can break a radical at a multiplication or division symbol. So instead of writing that as the square root of 4 times 30, I can write it as square root of 4 times the square root of 30. And then the square root of 4 is just 2. But I'm not done. Why am I not done? Still have to answer the question, right? The question wasn't finding that opposite side. It was writing the ratio for sine. So here I would say this is 2 square root 30 over 13. And what should I check before I say I'm finished? To see if I could reduce anything. Excellent. Is there anything to reduce here? No, right? Because the 2 and the 13 are relatively prime. Remember, we can only reduce inside radicals with something else inside a radical, and we can only reduce things outside a radical with things that are outside a radical. Everybody's cool? So this is what we would have wanted to write here. How do you guys feel? That wasn't so bad, right? A little bit different of a problem, but like, yeah, come on, guys. We're all right. Okay. Why don't you guys pull out your tablet? We'll take a bit of time here, maybe 30 minutes or so, and work on our little Delta Math assignment. Anything you don't finish on this would be something you could finish at home. So if you pull out your tablet, you go to your My Notre Dame page, log into the bulletin board. What you're looking for is the link on the bulletin board that says Delta Math. Notice while we're here that the video from last time is listed in the link section if you ever wanted to go back and watch that. But we'll hit Delta Math. You'll do your login. We logged in with Google. Pick your Google account. God bless you. You're welcome. And your screen looks different than mine. I think when you go and view your assignments, it says like it's late or something. I set it up. I thought we'd do this on the first day of class. Obviously, that didn't happen. That's okay. So if you click the assignments or whatever and you find that sample, just start in on that. Oops. That's not what I wanted to do. I don't know how to. Nope. Anyways, I can't look at it right now to show you what it's going to look like, but it's going to be a bunch of problems just like we did. The way it's set up, I think you get 2 tries per question, and you're finished when you've done 10 correct. And they're just going to randomly kind of give you some questions like we've just been reviewing. I'm going to walk around. If you have questions on things or you need some help kind of getting things set up, be happy to help. If you need to borrow a calculator, I have 4 here at my desk that you're welcome to grab and borrow. You can return when you're done. If we run out, you can always slide your desk up to a neighbor and share a calculator or something, right? Of course. Okay. So, chapter 1. What I've done here is I've taken all of the book pages from chapter 1 and the homework problems from chapter 1 and the odd solutions for chapter 1 and dropped them here into OneNote for you so you can see them all without having to download stuff and like have another window open. You can just kind of toggle back and forth between stuff inside of OneNote. Chapter 1 is going to be looking at a bunch of like review concepts from Algebra 2 now. And I guess I should say, or prior, because there's probably some stuff in here that maybe you didn't expressly do in Algebra 2 that might be even a pre-algebra kind of topic. But we just did our little geometry review. Chapter 1 is going to be kind of our Algebra 2 review. And then we'll kind of start building out our trigonometry pieces here, okay? So section 1.1 is about functions. Do we remember the definition of a function? Would be the fundamental definition from Algebra 2, since all you did in Algebra 2 was learn about different kinds of functions.
Having 1x and
Something.
I was literally thinking of that.
Sing it. Don't harmonize? Okay.
So we'd say that a function from a set D to another set R is an assignment or rule or pairing such that every element in D maps uniquely to an element in R. This set D has a name. We call that the domain. And this set R has a name. We call that the range. So again, for something to be a function, all of the x's have to be used, and they can all go, and they all have to go to exactly one y. Now they could all go to the same y, that's okay, but they can only go to one place. You can't have an x going to more than one place, or you can't have an x that doesn't go anywhere. So let's look at some examples. So let's say we just have like a little mapping diagram. So maybe we just have something that does this. Is that a function?
Yeah.
Yes, you guys are correct. What about this? Is that a function?
Yeah. Yes.
Yes, all the x's are used, and they only go, or they all go to one place. Still a function. Does it matter what's going on with the y's? No, it does not. Not all the y's need to be used, and the x's can all go to the same place. That is okay. How about this one? Is this a function? No, why not?
X is number Y.
Yeah, this guy didn't, that x didn't get assigned a value. Is that a function?
No.
No, why not?
We only have one.
Yeah, the last one goes to more than one place. Good. Everybody feel okay if we're looking at a mapping diagram and being able to tell if something's a function or not? Okay. What about if we have, say, an equation? I would say not enough information. Why? Most of you said yes, but you made an assumption in doing so immediately. So we'd say yes, and I would say that y is a function of f, or of x, but do we know that y is the independent variable and x is the, or y is the dependent variable and x is the independent variable from the way this is written? That's just our assumption, right? In Algebra 2, that would have been the case. But there's nothing about the way this is written to make it assume, or for us to know that x is the independent variable and y is the dependent variable. And if it was the reverse, if x depended on y, would it be a function? No. Why not? Because if you go and you get the x by itself, we'd subtract 2 from both sides. Then we'd have to square root both sides. And what do we have to have when we square root both sides of an equation? Plus or minus. So for example, when y equals 3, x would equal plus or minus 1. There's a case where one input has 2 outputs. So x would not be a function of y. So it depends here which one we're talking about is the independent variable and which one is the dependent variable. What's our domain set and what's our range set? Everybody's okay with that? So we do have to be specific here. Now, is there a way, a notational way to make it clear which one is the independent variable and which one is the dependent variable? Yes. What would it be? Yeah, so if we had instead written f of x equals x squared plus 2x, here it's crystal clear that x has to be the independent variable because we see that f of x, the other variable, absolutely depends on x. We've written it in such a way so it is expressly written that x is the independent variable. Everybody kind of see that? This is the slight difference between y equals and f of x equals, right? It's not, we don't impress that upon you in Algebra 2 because we use the two almost interchangeably, right? But there is just like the teeniest bit of difference, and that difference is just in the clarity of what is the independent variable and what is the dependent variable. So if we had written this instead of as f of x equals x squared plus 2, then you would have written instead f of x is a function of x. Absolutely. Does that feel okay? You guys see the difference? It's subtle, right? It's not a big deal, but it's like kind of a big deal. You know? It's just about being specific and really making clear what it is that you mean. Okay? So when you guys said that, yes, this was a function, that y is a function of x, how did you figure that out? You had to have done something, or you might have just guessed. You could have just guessed. That's okay. But probably somebody looked at that and went, okay, and then did something in their head to justify that this is a function. So I'd say there's a couple of things that maybe one of you guys would have thought about. If you look at this, does this look like a function you studied last year? What kind of function is this? That's correct. Say it loud. Thomas?
Quadratic.
Quadratic, right? Everybody recognize that as a quadratic function? So clearly it's a function. It's one of the quadratic functions. I knew it already. Very good. Alternatively, you might have looked at that and remembered there's a trick that if I knew what the graph of this thing looks like, I can tell whether it's a function or not. What do the graphs of quadratics look like? This is also something you could have remembered from Algebra 2. What does a graph of a quadratic look like? Go ahead. It is a parabola, yeah. What's a parabola basically look like? A U, right? So let's say we have some parabola. How can I tell if this graph represents a function? Do you guys remember this from Algebra 2? Vertical line test, yes. So what you're doing is you're just looking to see, is there any vertical line I can draw that would intersect the graph more than once? But no matter where I draw my vertical line, it's not going to intersect the graph more than one time, right? So we'd say that this passed the vertical line test. Everybody's cool? Alternatively, if we wanted to talk about this thing, the graph of that thing would have looked like that. Does that pass a vertical line test? No. Okay. What's the hitch about graphing things like this purple guy that I just circled on your calculator? Is that easy to do? Not really, right? If I wanted to try to graph this on my calculator, I'd have to use two lines. I'd have to do one as like square root of x minus 2, and then I'd have to do negative square root x minus 2. Because in function mode, our calculator can't graph anything that fails a vertical line test. Now, as the semester rolls on into pre-calculus, oh, my window is all jumped up. We'll look at some other ways of describing a function where you can have things that are still functions that fail vertical line tests. What? That's a pre-calculus topic for another day. So we're not going to go into that here, but you need 2 lines in your calculator to graph something like this. Is that okay? All right. And that, I would say, is section 1. Just about telling whether something's a function or not. I think there's 4 problems that we would assign there. And I'm going to stop here. Yeah, okay. Sophia.
Question. So let's say that like it's like x squared, like plus or minus a number. Would that?
Yeah, let's do an example. You have a what if example. So you have like, is this f of x equals or y equals or?
Like y.
Okay. X squared, and you said plus or minus. I'm just going to write 1. Okay. And then we want to know, is y a function of x? So let's be specific and just say the one that we intuitively would know, right? That x is the independent variable, y is the dependent variable. Not super obvious right away, right? Let's just pick a value for x and plug it in and see what happens. 3, okay? So when I plug 3 in for x, so I get y equals 9 plus or minus 1. So 9 plus 1 is 10. 9 minus 1 is 8. So we're getting the points 3, 10 would be a point on my graph, and 3, 8 would be a point in my graph. Is that a function? No way, because we have one x coordinate, 3 that goes to 2 different y coordinates, 10, and also to 8. Does that feel okay?
Yeah.
So the plus or minus is usually a great indicator that like, that ain't gonna be a function. Is that sufficient explanation? Again, you could graph this on your calculator, but it would take 2 lines to do it. You could do x squared plus 1 in one line, and then x squared minus 1 in the other line, and you'd look at this all together as one function, or one graph. This is all one. Both those curves are this graph, and you can see right away that's going to fail the heck out of a vertical line test, right? So regardless of kind of how you want to conceptualize that, any of those methods that we just kind of ran through would be excellent explanations as to why this would not be a function. I personally like just picking a point and showing that, hey, 1x gives me 2 y's. Bad news. But, you know, if you like thinking about it as a mapping diagram, or you think about it as drawing the graph, or whatever you think is easiest conceptually, is okay with Mr. Kulik. And I think this is probably well, we'll start 1, 2. We can do like one topic in here, and then we'll leave off. 15 minutes is a little bit too much to just punt on. All right. So 1-2 is going to be about domains and ranges. But before we talk about domains and ranges, we want to talk about interval notation. Okay. What does you guys used interval notation last year in your Algebra 2 class, right? What is interval notation describing? Go ahead.
Doesn't it describe like domains or like
Well, you can use it to describe domains and ranges, but it's something more than that. So an interval notation just describes a set of continuous values For example, say you want all the numbers between, maybe let's be specific, we'll say real numbers between 7 and 13. So if I wanted to describe that as a set, I'd say the set of x is such that 7 is less than x, which is less than 13. Right? Now, that's kind of a clunky notation. Last year, we'd have written just 7, 13 with parentheses at the end. Right? And if we said all the real numbers between 7 and 13, including 7, but not 13, our set would have looked like this. So our interval then would have had bracket 7, 13 with the parenthesis. You guys remember doing this kind of notation? Say all the numbers, be specific, Kulik, real numbers less than 5, including 5. How did I write this interval? Sure, no problem. We're drifting. Nolan? Excellent. Now, if you're stuck on where to start with something like that, I think it's often helpful to just kind of think about it on the number line. So here's 0, here's 5, and we're talking about all the numbers that are less than or equal to 5. Everybody's okay with that? So if I look at the stuff that's covered, negative infinity up to and including 5. So again, I'm a visual person. I think that it's super easy to write the interval correctly once you have a picture on the number line. And sometimes if I'm stuck as to like, ooh, how would I write that interval? Drawing a picture on the number line can be awfully helpful. We'll do 1 or 2 more examples and then call her a day. How's that sound? Okay. Oops. So here we have all the real numbers that are less than 6 or bigger than 7, including 7. So maybe it's helpful to draw this. For starters, oh my goodness, what is going on? So all the things that are less than 6, notice that I'm drawing that with an open circle. And then the things that are bigger than 7, including 7, well, that'll get the closed circle.
What's the difference between open and closed?
So the open means we're not including 6, right? And the closed means we are including. It's basically the difference between a less than versus a less than or equal to. Yes?
What's the difference between the bracket and the parentheses?
The bracket means that value is included in the set,
Okay.
and the parentheses means it is not. And since like an infinity is not a specific number, the infinities always get a parenthesis.
Okay.
Okay, sure. So if we look at this, we would write parenthesis, negative infinity, up to 6. Then we have a gap, right? Because there's nothing is covered between 6 and 7. Then we'd have 7 with a bracket to positive infinity. And you guys remember the symbol that we use to connect two intervals that are or? Yeah, it's the U symbol. This is the symbol for union.
So for the 6, if it was like less than and equal to, then it would be like
A bracket. And a solid circle with a bracket. Absolutely, yes. All right, one more example and we'll call this done.
what's the last number?
26. So we have all the numbers between 7 and 10, including 10, and then also 26. So I'll just kind of start by drawing us a picture. Oops. Let's see, we'll call that 7. That'll be 10. There will be 26. So we'll go 7 to 10. And we also have 26. Is everybody okay with the picture I drew? Does that make sense so far? Okay. So 7 to 10. 7 gets a parenthesis because it's not included, and 10 gets a bracket because it is. Oops, I should have used the word or here rather than and. I'm going to edit that. My apologies. Want to be technically correct. Okay, but how do I include that just the 26? Well, is that a continuous amount of numbers? No, that's just one single number, right? It's not like all the numbers between two values. So should we use interval notation to describe that? No, that's just another set, right? Just a set with one value. So we'll just use the set brackets to describe that. Be for finite number of values. Well, hold on. Nope. Let me be clear. Could be infinite still, but for a discontinuous values. So, for example, if you had like all the odd numbers, there's an infinite number of those, but they're not continuous because there's gaps in between every odd number, right?
Good afternoon.
So if you have a finite list or a discontinuous list, you have to use that other notation. Sophia, don't forget your stylus.
Let us reflect on our day today.
I just wanted to, before I
What
forget.
is one thing that you are most grateful for that happened this day? Lord, thank you for the gifts of the people and the things that happen to me throughout my day. And allow me to continue to carry that forward in all that I do this evening. We ask this in your name, amen. In the name of the Father, and of the Son, and of the Holy Spirit, amen. Have a good day, Notre Dame and Mary.
If you borrowed a calculator from me, make sure you give it back.
Thank you.
You're welcome. 1 second. So there's the delta math,
Yeah.
but nothing else is due. So everything else is the Sunday's problem set. So I think I've assigned, you could do the first four problems at this point, but that's it. Nothing is due yet.
Thank you.
So for this question, would it be yes or no? Yes? Isn't that because, like, if you take the square root, square both sides, then it would be y squared plus 5?
It's because if I pick a value for x, it's 5 or more.
Yeah.
All I get is one value for 1.
Okay.
Any value of x you pick, you just take the square root.
Okay. Alright, that makes sense.
Is that okay?
Yeah. Thank you.
Do you need the rubric for discrete? I kind of printed that on the side.
Oh, I think I put that on as a mistake. I don't need a or sign something from you guys. Yeah, I think I deleted that back off. If I didn't, we'll do it next time.
Got it.
Just remind me.
Sounds good. All right. Thank you.
You're welcome. Bye. You're welcome. We'll do some more practice with this next time. Don't feel like you need to be an expert right yet. Have a good day.
She was like working on it. And then she was like, thank you.
You're welcome. Bye.